All right, so we're going to switch to our next chapter here. And this chapter is going to be talking about substitution and elimination reactions of alkyl halides. All right, so let's remember what an alkyl halide is, right? So alkyl, meaning we have an alkane, but an alkyl halide is then one with a halogen on there, right? So something like chlorine, bromine, or iodine. All right, these are going to undergo reactions with nucleophiles, and I'll talk about this here in a second, but we're going to use this N kind of like a variable. And there's going to be two products that we're going to see, and we're going to learn this whole logic behind which product's the major product and which one's the minor, okay? But just to kind of introduce things, these two products are either going to be the substitution product, where that halogen gets substituted for that N, that variable. These are what we call substitution reactions. Okay. As well as an elimination product, which is which functional group? What do we call these things here? An alkene. Okay, so we can get one of two products in these reactions, starting out with an alkyl halide. You can either get the substitution product, where we just swap out that chlorine or that halogen for this nucleophile in our reaction. Or you can get an elimination product, which is where you have this alkene that's formed, right? So you eliminate that chlorine altogether, giving you this alkene product. All right, so some terminology here. Again, this is what we call a nucleophile. All right, picking that word apart, a nucleophile is something that loves the nucleus. That's sort of just picking apart the name, right? Nucleophile loves the nucleus. Importantly, these are electron-rich species, and they're very attracted to a positively charged nucleus, right? So the basis of reactions in organic chemistry is something has a bunch of electrons. Something else really wants those electrons, right? And that's the sort of basis behind all reactions in organic chemistry. Our nucleophile is this electron-rich species, so it's going to want to find and react with things that are relatively electron deficient. Okay? So again, nucleophile means that it's electron-rich. We have another term, electrophile. Okay, these are things that love electrons. And they really want electrons because they are relatively electron deficient. They're electron poor. All right, so we're going to see this over and over again in organic chemistry. Nucleophiles react with electrophiles. Again, things that are relatively electron rich will react with things that are relatively electron deficient. The electrophile in these reactions is the carbon at the base of that halogen. Right? These halogens are very electronegative. They're really good at stealing electron density from atoms that they're bound with. Right? And so in this case, this carbon at the base of this halogen is our electrophile in this reaction. Okay? Because of this carbon-chlorine bond right here, that carbon is relatively electron poor. That chlorine is stealing the electrons away from that carbon. All right, if you were to look at the electron density in a reaction or in a molecule like this, you would see a lot of electrons sitting on that carbon and on that chlorine, and very few sitting on that carbon. Okay, because again, chlorine is very electronegative. What that means is that it steals electrons in this bond. Okay, so we can just say chlorine is electronegative. Let me make room for all this. It's called electronegative, which means it steals electron density from carbon. All right, again, leaving that carbon relatively electron poor, which is why it plays the role of the electrophile in these reactions. All right, so the nucleophile is this thing in our reaction, and we'll see a bunch of examples of different nucleophiles. Our electrophile is the carbon at the base of that halogen, and again, what we're going to see is this reaction between our nucleophile and that electrophilic carbon. Okay, we got one more term, which is for the halogen itself. We call this a leaving group. Called a leaving group because in this reaction it gets kicked off, right? It ends up leaving in this reaction. All right, so let's see a specific example here. I'm going to use a specific nucleophile, so I'm going to use the hydroxide ion. All right, and again, we're going to get two products. One where I'm going to substitute that nucleophile for my halogen, right? So I'm going to replace that chlorine with an OH group. And another one where we have our elimination product, which is again just forming an alkene. Okay. So I want you to take a minute and identify the nucleophile, the electrophile, and the leaving group in this reaction. All right, so my nucleophile would be the hydroxide ion, okay? We're gonna see that a lot of nucleophiles have that negative charge associated with them because, again, nucleophiles are electron rich. That's what it means to be a nucleophile, right? So having that net negative charge, good indication that we have an electron rich species. Our electrophile is the carbon at the base of that halogen. And finally, the leaving group is that halogen itself. That's what's being kicked off in this reaction. Okay, and again, these reactions have these two products, the substitution product, and the elimination product. All right, and by the end of this chapter, by the end of this week, we're going to be able to look at a reaction like this and determine what is the major product, the substitution product or the elimination product. There's going to be this whole logic. It turns out, we're going to see that some alkyl halides will prefer a substitution product, whereas other ones prefer an elimination product, right? There's going to be this logic behind how we determine the major product. But the first thing we're going to do is just look at each reaction type separately, right? And then we'll roll all this together, okay? So what we're going to do first is focus on these substitution reactions. All right, so again, we'll talk about the competition between the two types of reactions here in a bit, but first we're going to just focus in on these substitution reactions. All right, again, we're going to have an alkyl halide. We're going to be reacting it with some nucleophile, some electron-rich species. And we're going to be substituting that leaving group, that halogen, for our nucleophile in this reaction. I want everybody to take a second and see if they can't predict the product of this substitution reaction based on analogy on what we did last time around with the hydroxide ion. All right, how many carbons should be in my product? 4, the 1, 2, 3, 4 that I start out with, right? So again, count carbons, easy way to double check. So I should have these 4 carbons, and then I'm going to substitute my chlorine for this nucleophile here. In this case, it's this SH group. All right, and again, we get lazy and we don't draw it, but if I wanted to draw a balanced chemical equation, I can show that that chloride ion is being kicked off. All right, again, you'll just focus on drawing your organic product as we've discussed before.
Where does the negative go on the product?
Yeah, that's a good question. So notice how our negatively charged nucleophile gets attached to our carbon and it like loses that negative charge. Okay? This pair of electrons here actually is what forms this new carbon-sulfur bond. That's where that pair of electron goes. It goes from being a lone pair on the sulfur to actually a bonding pair of electrons, a covalent bond. And you can see that we have this conservation of charges, because on the left-hand side we have a negative charge, and on the right-hand side we have a negative charge, right? So there's no electrons that aren't being accounted for here. But yes, we're going to see that these negatively charged nucleophiles form this new bond and, kind of lose that negative charge. Really, that negative charge becomes that new carbon nucleophile bond. But yes, good question, because that's where we're going now, is now looking specifically at negatively charged nucleophiles. Okay. And we're going to see a bunch of different ones. Okay, and importantly, that atom with that negative charge, right, it's the sulfur that has that negative charge. Notice that it is the sulfur that is then bound to that carbon. All right, so let's look at one that's a little bit more complicated. What if we had, for example, something like this, and this oxygen here with a negative charge that's now attached to two carbons. All right, take a second and see if you can't predict what the product of this reaction would be. All right, again, it's the negatively charged atom. In our nucleophile that forms a new bond with that electrophilic carbon, with our electrophile. All right, so again, this was our nucleophile. The carbon at the base of that halogen, that's our electrophile. And I'm going to form this new bond with my negatively charged oxygen. And then I'm going to include those two carbons on there. Kind of ran out of room.
Does it matter which way that group is pointing?
Right. Like if it was over here?
Yeah.
Yeah, no, it doesn't matter. All right, so again, I have this new, what's up?
Does that mean a lot, like the line, obviously like the methyl that was sticking out, for example, like does it, like if it's not touching the oxygen, like does it mean a lot, or touching it, like both sides, the lines, like does it mean anything different or something like that? Or would you mark it wrong or something like that?
So what do you say it again?
Like the
You mean if you put your oxygen up here, maybe?
No, the oxygen that's in the middle in between, like if it's touching the actual oxygen, like if you connect them all together, like that little space in between the.
Oh, okay. I see what you're saying.
You have to do a whole like yeah.
So something like this, and then you put your oxygen. I mean, it's just a little slot. It looks a little messy.
Yeah.
It would look weird. I don't know that it's not like I don't necessarily understand what you're saying, but yes, at this intersection, we don't have two lines touching because that would be a carbon, right? So instead we have an oxygen in that place. Okay. Again, the whole shtick here is that we formed a new bond between that negatively charged atom, that oxygen, and our electrophile in this in this compound, the carbon at the base of that halogen. Okay. We don't talk too much about mechanisms in this course, but just kind of out of curiosity, what happens? This pair of electrons in this negative bond reaches out and grabs this carbon, and that in turn kicks off that leaving group. Okay, this mechanisms aren't something that I'm expecting you to know, but just FYI, in case it's curious as to how exactly this new bond is being formed. All right, so let's do another one. You're going to give me the product of this reaction here. All right, so again, I just need to identify what my new bond's going to be. It's going to be between this negatively charged oxygen, right, my nucleophile, and my electrophile, the carbon at the base of that halogen. That's what my new bond's going to be. All right, so starting off with my product, I got my 6 carbons from my ring. It's going to be a new bond with that oxygen, right? That's my blue oxygen that had that negative charge. And now I just need to make sure to include everything else that was attached to that oxygen, right? So I have this here, carbon-oxygen double bond. What do we call those carbon-oxygen double bonds? Carbonyls. Awesome. Kind of ran out of room, but and just make sure to include all 1, 2, 3 carbons from my nucleophile in my product as well. Whoops. All right, so again, for these negatively charged nucleophiles, that negatively charged atom in the nucleophile is what forms the new bond with our electrophilic carbon, our electrophile.
Would it matter if on the nucleophile, the O would be on the right side instead of the left side?
Say it one more time.
On the nucleophile, would it matter if the oxygen will be on the right side instead of the left side. On the right hand.
Well, so importantly, this oxygen has to be what's attached to the ring, right? So you can't have attached like this portion of the molecule to the ring. Was that your question? So basically, you could have drawn this same structure in like a different orientation. So maybe like this oxygen pointed up here. Something like that is the same thing. But importantly, that oxygen has to be the thing that's now attached to the ring. It would be incorrect to have it look something like that. Okay, the oxygen itself, that negatively charged atom, right? So the negatively charged atom, which is in this case that oxygen, has to be what's forming the new bond with that electrophile.
In this class, where there be a situation where, let's say, there'd be two negative
No.
charged atoms? Okay.
Nope. Okay, so I'm just going to put down 2 more examples, and I want you all to give me the product here. The substitution product in particular. All right, and count carbons. Make sure you have the correct number of carbons on both sides, or rather the same number of carbons on the right side as you had on the left side. All right, so first of all, just because y'all will see this a little bit more, this is, the sort of full Lewis structure of this thing right here. This is what's called a cyanide ion. Has anybody ever heard of cyanide before? In what context? Poisons, exactly, right? So super, super toxic substance is cyanide. Importantly, what you'll oftentimes see this more abbreviated as just CN, right? This is kind of that full, I guess if I was being good, I can put in my lone pairs. This is sort of the full drawn out Lewis structure this is this abbreviation, not unlike that nitro group, right? NO2 we see abbreviated, it's not drawn out in its full Lewis structure all the time. Importantly, we can note that that negative charge is on the carbon, right? So like we said, that negatively charged atom, that carbon, is what's going to form a new bond with my electrophile, the carbon at the base of that halogen. All right, so if I'm going to draw my product, I'm going to have 1, 2, 3, 4, 5 carbons from this side. Okay, and then I'm going to stick on that cyanide group. Okay, if you drew the triple bond explicitly, that's cool too, right? But again, you'll see it in this condensed form. Importantly, it's the carbon that's attached, right? So what would be incorrect would be to draw it like this. All right, it's the carbon that's attached to that electrophile, not the nitrogen. So again, this negatively charged atom is forming a new bond with what we call the electrophile, right? The carbon at the base of that halogen. What's up?
I have a question for the CNN group that you just added.
Uh-huh.
In our homework, how would we put the CNN? Do you know if it would change on its own, or do we have to like? Because on the homework.
This
it-
last one, I put it like that, you had to draw.
Yeah, you probably have to draw the thing out, the
Okay.
triple bonds.
Sounds good.
Yeah, because they don't let you abbreviate carbon. All right, so in this case here, again, my new bond is going to be between the negatively charged atom in my nucleophile, in this case sulfur, and the carbon at the base of that halogen, our electrophile, right? And so we can see that our products can get kind of big and ugly. We just got to remember our double checks. We can count carbons, right? So I'm going to draw my original molecule. This would have been that electrophilic carbon. So now I'm going to put in that new bond between my electrophile and that negatively charged atom in my nucleophile. And then I'm going to make sure to include those 3 carbons that were attached. Boom. What's up?
Does it matter what direction the branches go? Or like we draw it to the side?
Like you drew it like over here? Yeah, that's fine. All right, really, if we were being good, it's true. It wouldn't be straight down. It would be something like that. But yes, doesn't matter. All right, so again, negatively charged nucleophiles, that negatively charged atom in our nucleophile forms a new bond with that electrophile, that carbon at the base. We just say carbon at base of our halogen. All right, and then we'll see some reactions that have not negatively charged but neutral nucleophiles. Actually, oh, that's fine. All right, so I drew it out kind of explicitly like this, and I'll explain why in a second, but what molecule is this? Yeah. right? This is just water. I've kind of explicitly drawn out one of those oxygen-hydrogen bonds for a reason here. We'll see in a second. Okay, so my product here is actually not going to be the whole H2O, but just OH on there. All right, so if I was being good, I would show that my other product in this case was HCl. But importantly, notice that my nucleophile here, we still call it a nucleophile, water, forms a new bond with our electrophile, the carbon at the base of that halogen. And we still kick off that leaving group. Okay, so same as we saw before, but now we have this neutral nucleophile. Our neutral nucleophile, we're going to see that that hydrogen is lost. From the heteroatom in our nucleophile. Okay, what the heck do I mean by heteroatom? Basically anything that's not carbon, right? In this case, it was an oxygen. Importantly, carbon's not going to ever lose its hydrogen. It's always going to come from like an oxygen or a nitrogen or a sulfur, one of these heteroatoms. So not carbon, but oxygen, nitrogen, sulfur, etc. Something that's not carbon. So a hydrogen is lost from our heteroatom in our nucleophile and replaced with that new electrophile bond. Right, so my oxygen is what's forming that new bond with that electrophilic carbon. That oxygen loses a hydrogen and gets a new bond with that electrophile. All right, so let's just practice this. All right, so for this one here, this top example, all right, I'm going to start out with my original 5 carbons in a ring, and then what is my new bond going to be between my electrophile over here and which atom in my nucleophile? The oxygen. All right, and that oxygen is going to lose that hydrogen. But still have those 1, 2 carbons on there. All right, so again, our hydrogen is lost from that heteroatom, from that oxygen in our nucleophile, and it's replaced with a new bond with that electrophilic carbon. All right, notice in all of these examples, that's what we're doing. We're creating a new bond between that electrophilic carbon, that electrophile, and whatever is in our nucleophile. All right? All right, so then for this one here, again, I'm going to start with my benzene ring. I'm going to try to draw it a little bit smaller because I can tell I'm going to run out of room. Okay, and here's my electrophilic carbon, the one at the base of that halogen, and it's going to form a new bond with which atom? The sulfur. And again, that sulfur is going to lose a hydrogen, so it's going to be just SH in my product, right? Not SH2, because it's got to lose one of those hydrogens.
Will it only ever lose 1 hydrogen?
Only ever lose 1 hydrogen, yep. And it's always going to be a hydrogen that it loses.
I don't know if this even matters or if you did it intentionally, but if you move the double bonds, does that even matter? Like, will it change?
Oh, no, yeah, you're right. I didn't do it intentionally. But no, it doesn't matter, right? Because these double bonds, remember what we learned last time, they're kind of always moving around in a circle here. So yeah, you can shift them all one position and it's equivalent. All right, so now let's just practice this for the rest, right? So again, what we're going to see is these substitution reactions are in competition with elimination reactions. But again, we're just kind of focusing in on that one type for right now, just focusing on these substitution reactions and predicting products. All right, so in the last little bit here, let me just put down a bunch of examples. All right, and so let me just say one more thing about this. So this one might look a little bit different than what we've seen before, NaOH. But importantly, whenever you see something like sodium, really any one of those first row elements, so, or rather first column elements, let me just bring up a periodic table real quick. Okay, ignore all this, not this class. Lithium, sodium, potassium, rubidium, cesium, okay? These are all what are called counter ions. So when I see something like sodium hydroxide, for example, in my mind, I immediately erase that sodium and put in a negative charge, all right? In sodium chloride, the sodium ion is a counter ion. Never participates in the reaction. It's just kind of floating around watching the action happen, right? Its whole goal in life is to balance this negative charge. It's positively charged. It balances the negative charge on that hydroxide ion. But again, whenever you see something like NaOH in your mind, you immediately just erase the Na and put a negative sign in. All right, so in the interest of time, I'm gonna quietly put these up on the board, so if you're stuck, you can look up, but you wanna try to work through them as best you can on your own. All right, so this sodium, again, when I see that, I'm going to erase it and replace it with a negative sign. So these are these negatively charged nucleophiles. I'm going to attach that oxygen to my electrophilic carbon in my product. Same thing down here. I see this sodium, and in my mind, I erase it and replace it with a negative sign. So again, I have that electrophilic carbon forming a new bond with that nucleophile. And the other two, they're neutral, so it's going to be the heteroatom with that oxygen that gets attached to my electrophile in my alkyl halide. Cool.